Space is an environment where standard computing fails. Our solar system is constantly flooded by high-energy cosmic rays and violent magnetic eruptions from the sun. When one of those particles strikes a silicon microchip, it can instantaneously alter the electrical charge in a memory cell. This is a bit flip, an event that turns a 0 into a 1 in the middle of a calculation. A single bit flip on a satellite in low Earth orbit can scramble telemetry data, causing multi-million-dollar gyroscopic stabilization systems to fire incorrectly and send the craft into an uncontrollable spin. Traditional electronics rely on delicate electrical charges that are inherently poorly suited for the radiation-heavy reality of off-world travel. To prevent these errors, engineers currently wrap standard integrated circuits in heavy, expensive radiation shielding or use complex cryogenic systems to keep the hardware stable. This added weight limits spacecraft design and increases launch costs, while the sensitivity of the components complicates the operation of Martian rovers and deep space probes. But there is a way to avoid these failures without adding mass. Instead of relying on electrons, we can build a control system out of sound. Replacing electrical charges with mechanical waves offers a physical path to hardware that is immune to radiation by design. This concept led to Vortex-Q Ambient, a hardware architecture born from a physics exploration by a researcher named Brody and an AI named Grok. This architecture works by moving away from the standard practice of pushing electrons through straight silicon paths. The system is built around toroidal or donut-shaped piezoelectric loops. When these loops are stimulated, they generate macroscopic acoustic phonons. These are organized, large-scale vibrations that move through the material, effectively replacing electrical signals with physical ones. By computing with these vibrations, the system translates data into a physical state that is far more durable than an electrical charge. While radiation can easily knock an electron off course, it has almost no effect on a mechanical vibration traveling through a solid structure. Because information is stored in the frequency and shape of the vibration, a high-energy cosmic ray passes straight through the material without altering the data. This makes the hardware radiation-hardened at the fundamental level, removing the need for any external lead or tantalum shielding. This immunity allows for the creation of attitude control and positional monitoring systems that stay stable through the worst solar flares. By using the phonon as the primary medium, the system ensures that bit flips are no longer a factor in aerospace navigation. Satellites and lunar rovers can now discard heavy shielding, making them lighter and more reliable for long-term missions. The technology also integrates with the Imagenta hybrid platform to address challenges outside the aerospace sector. Vortex-Q Ambient uses advanced TFLN transducers to convert these acoustic waves directly into optical signals, acting as a bridge for microwave to optical conversion. This conversion capability makes the system a practical tool for scaling quantum networking, as it allows quantum information to move between different physical formats without losing coherence. Because these vibrations occur at such high speeds and require very little energy, the architecture can also power sub-nanosecond photonic neuromorphic computing. This allows AI to run on edge devices with minimal power consumption. The same mechanical principles used for space navigation are now being applied to over 20 different fields, including underwater sensors and autonomous drones. What began as a question about solar flares has resulted in a hardware architecture that keeps satellites stable, enables quantum communication, and runs AI more efficiently than silicon ever could.